section 13.2, vectors and matrices in data mining. It's often the case that the data are numerical and the data points can be considered as vectors in a higher dimensional vector space. Stacking of such data points can be organized as matrices. In such cases, it's natural to use concepts and techniques from linear algebra. Here we present a modification of the paper, Numerical Linear Algebra in Data Mining. If you are interested in numerical linear algebra aspects of data mining, then the paper will be a good source and try to read it. It is a really good paper. In this section, we'll consider two algebraic examples in data mining, text mining and Google PageRank. Details of the algebraic properties will be discussed in the following sections. Let's see the first example in text mining. Here we'll consider so-called term document matrices. They are used in information retrieval. Consider the following set of 5 documents. Document 1, 2, 3, 4, 5. We assume there are 5 documents available, and each document here has such sentences. And now the keywords referred to as terms are marked in boldface. In this text mining, we try to find documents having the keywords in query, so that by assuming we have only 5 documents in the internet, by using some query, you can find the relevant documents. Okay, here. Now, for these documents and the sentences in the document, and we try to count the frequency of terms, and then we can get a following result. For example, document 1 has the keywords here, this, that, so that once you have terms, that is called the dictionary, and now in this ordered in this way. Now here, that is has Google, the term, and a metric, or an internet here, and then metric. In this way, you try to count the terms in each document. Then we can get such metric. Now, each document is replaced by a vector in R10. So for example, document 1 can be represented by this one. For the given set of keyword, that means dictionary, the document 1 has such a vector. So it is a representing vector for the document. So that is what it is saying. And we can organize the data as a term document metric. We consider only this numeric part. Then that is the term document metric. Now we consider a query ranking of web pages. Then, now this query can be also represented by a vector. Now, rank web page, that is now in the dictionary, we have a page rank web, so that for the query, this last 3 will be 1. So that is exactly this one. Okay, so the code itself can be considered as a document in a sense. But anyway, and code is a vector, and also each document is again a vector. So there's reason it can be considered as a document. Okay. Now, the information retrieval task can be formulated as a mathematical problem. The problem is find the columns of A, columns of this, the term document document metric, and that are close to the vector Q. That means that the documents will have the terms, so that is now the idea of text mining. To solve this problem, we use some distance measure because already we consider the closeness, so that we have to have a distance measure. Information retrieval with a term document metric can be considered in this way. It is common that n is large, so n by n metric, so the number of terms is large, in the order of million, and the metric A is sparse because most of the documents only contain a small fraction of terms in the dictionary. In some method for information retrieval, linear algebra techniques such as singular value decomposition are used for data compression and now retrieval enhancement. So we'll see at the end of the chapter one example that uses, in fact, the next section we'll see one example using the singular value decomposition. The very idea of data mining is to extract useful information from large and often unstructured data sets. So the method must be efficient, and also it must be designed for dealing with large problems. Now let's go to the second example, which introduces also an algebraic system. So this is the second algebraic example. It's about Google's PageRank algorithm. Its main task is to sort the internet web pages found by search engines. So in fact, Google search engine is doing the finding the web pages and sort. Okay, the two things are happening simultaneously. But anyway, the sorting is requiring some more critical mathematics. The core of the Google search engine is metric computation, probably the largest that is performed routine. The reason is the dimension of Google metric is about 10 or 100 billions. Some many years it is order of billions, but now I believe it must be tens of billions or 100 billions. The Google metric P is assumed to be of dimension of the order billions in 2005. But nowadays, I believe it will be much larger. In the Google PageRank algorithm, the problem of assigning ranks to all the web pages is formulated as metric eigenvalue problem, which is the the topic in the last section of the chapter. Okay, we'll see a little bit of the link metric, so that link metric will be used later for Google metric, and that will along with that, the page rank algorithm is formulated. Okay, let's begin with this one. Let all web pages be ordered from 1 to n. There are n web pages, and I is the particular web page, ith one. Now, OI is denoting the set of pages that I is linked to. So our linkers. That means that an ith page has some the linkers inside. Then if you click the link, then it will go to some other site. That kind of a link is called our linkers. And the number of our link is denoted by now ni. So ith here, the page, web page has ni outlinkers. The set of inlinkers denoted by ii are the pages that have an outlink 2i. So that this ith link, if you think inlinkers, then the ith link has no idea. However, from outside, and the ith link is linked so that they can come from outer the linkers. Such links are called inlinkers. Now, denote Q to be the square matrix of dimension n, and so that here, if there is a link from J to I, then that is now one of nj. So that now we consider the nj as for jth web page, the number of our linkers in the jth web page. Okay, otherwise it's 0. Okay, if I try to explain algebraically, then it's hard to understand. Let's see the graph. That is now link graph. Assume now number 1 web page has our link, and to 2 and 4, there are all 6 web pages. And number 1 has our links to 2 to 4, 2 and 4. And for example, fifth web page has now, okay, 1, 2, 3 our links, and now 1, 2, 3 in links. Okay, in this way, you can understand. Then look at here. Now, first web page has now 3 outlinks. That is 2, 4, 5. So that 2, 4, 5 equally, the weight is given equally. Once somebody comes here and try to go to next website, then we assume that it has equal the probability to go to the next website. So that for number 1 website, we have this column along with our links. Now again, think of this one, 1, 2, 3, 4, fourth one. Look at over there, fourth one. For fourth one, there's no our link, so that 0. And for example, the last one, it has here 2 our linkers from 6 and 5 and 3. That is exactly 5 and 3. So there are only 2 out linkers, so that here equally, and 3 and 5 has half possibility. So in this way, we try to formulate the link matrix. There's a link graph. the corresponding link metric becomes this one. So there are n websites, then the link metric must be n by n. So over the world, currently more than 100 billion, I guess trillion websites, so that Google metric has dimension trillion. So it's really a big metric. Now we define a PageRank vector R, which holds the ranks of all pages. So the summation of R, the entry, will be 1. So it is a kind of a probability vector and non-negative. Each entry is non-negative. Now the larger is ranked higher, so that when the Google is visualizing the website found, along with from the highest one, it is shown to you, so that more reliable pages can be seen earlier. That is what PageRank algorithm is doing. Once we define R, then the vector R can be found as the eigenvector corresponding to the eigenvalue problem. QR equals lambda R. So lambda is 1. So we write down here lambda, but lambda must be 1. Now, so the R will be an eigenvector of this the metric, but in fact, for such a metric, link metric, along with this metric, there's no guarantee for the eigenvalue 1, and possibly such Q may not have eigenvalue 1. Or even though it has eigenvalue 1, the question is, now eigenvector must be unique. If not, then and eventually we cannot use the result very effectively. So that the realistic formulation of PageRank equation must be followed, and then now some numerical aspect of this PageRank computation is also not trivial. So later on we'll consider these issues in section 13.4. Okay, that's the end of the section. Thank you.